Hello everyone. Today we're going to be working on example 7.1.4, and this example is asking us to determine the normal force, shear force, and bending moment acting at point B of the frame. So as you guys could see, this frame has two components to it, two members to it, which would be our member AC and our member CD, which are being joined together by a hinge support at point C. So, since this is asking us to determine the forces and the moment at point B, we know that at point B is where that cut will be going. Then taking this frame into two pieces now. So before we find anything, the first step that we want to do is we want to take a look at both sides of this frame to determine which side of the frame would be easier to work with. So if we were to take a look at this side of the frame, because once we cut it, it would be this part of the frame and then this part of the frame. So taking a look at this part of the frame, at point A, we have a fixed support, meaning that we're going to have three unknown reactions. We're going to have our moment, we're going to have our vertical reaction, and our horizontal reaction. So if we were to work with this side of the frame, we would have to find the three unknown reactions. Now looking up on this side of the frame, if we were to work with this part of the frame, we could see that at point D, we have a roller support, meaning we're just going to have one unknown reaction, which would be our vertical reaction. So by taking a look at this, as you guys could see, I would prefer working with this side of the frame because we would only have to determine the value of one unknown reaction. Meanwhile, with this side, we would have to determine three unknown reactions. So to find the value of my reaction d sub y, what I'm going to start off is I'm going to do a break of the structure at the hinge, and then I'm going to be, so right here, I'm going to be breaking this structure up right here at the hinge. So let me draw that out. And then we're going to have our loading. And then from there, we have our hinge right here. And then from there, we know that this loading has a loading of 400 newtons per meter. And we know that we have our roller support right here, which I'm assuming that the reaction will be going upwards, d sub y. So we know that at a hinge support, we know that it's kind of the same as a pin support. So we know that there's usually two reactions right there, our vertical reaction and our horizontal reaction. But I don't really want to deal with those. So what I'm going to do to determine the value of my reaction d sub y, which is the one that I really need to find to then determine the normal force and shear force and moment at point B, is what I'm going to be doing is I'm going to be taking the sum of the moments about that point, point C, which happens to be where our hinge support is. And since I'm going to be taking the sum of the moments about point C, we know that those reactions of the hinge will not be creating a moment. So that way I would simply just be solving for my reaction d sub y. So we know that this part of the frame has a span of 4 meters given to us right here. So the first thing that we have to do before taking the sum of the moments about point C is first determining the concentrated force of this loading. So to do that, I'm going to call this F of 1, or you could call this R sub 1. It doesn't really matter. But what I'm going to be doing is I'm going to be getting multiplying 400 Newton meters by the span of the whole loading, which happens to be the whole member, so 4 meters times 4 meters, and that should end up giving you 1,600 newtons because we could see that our meters would cancel out. And we know that we're going to find this, the location of this concentrated force is going to be right mid-span of that whole distributed loading, since it is, as you guys can see, it's like a uniform loading. So that's why we know it's going to be found right in the middle. So we have 1,600 newtons acting downwards right there. So since we know that the this member has a span of 4 meters, which is also the span of the whole distributed loading, we know that we have 2 meters on this side and then 2 meters on this side. So now that we know all of that, now I'm going to be taking the sum of the moments about my point C to determine that value of our reaction d sub y. So counterclockwise, positive, we know that the sum of our moments about point C have to equal 0. Sorry, hold on, guys. Counterclockwise, the sum of our moments about point A. No, ooh, sorry, point C have to equal 0. Okay, there we go. We know that once again, the reactions of that hinge support will not be creating a moment. So then from there, we have our concentrated force. It is going downwards and it is to the right of that point. So we know it's going to be creating a clockwise moment, meaning a negative moment, force of 1,600 newtons with a distance. We know that that this can be found a midspan. So we know that from here to here, there's a distance of 2 meters. And then from there, the other force that's going to be creating a moment is our reaction d sub y. This one is going upwards, or I'm assuming that it will be going upwards. So we know it's going to be creating a counterclockwise moment, meaning a positive moment. We have the force, that's what we're trying to determine, and we know that from our reaction to the hinge support, there is 4 meters. There's a distance of 4 meters. From here, we would simply just be solving for our reaction d sub y. So we end up getting that our reaction d sub y has a value of 800 newtons. And since we got a positive number, that means that we assumed correctly the direction of our reaction. So we do know that that reaction will be going upwards. So now that we have that, now we can proceed to drawing now the side of the frame that we're going to be working with to determine the normal force, shear force, and bending moment at point B. So that's what I'm going to be doing. I'm going to be drawing the free body diagram of it. So free body diagram. And remember, we said that we were going to be working with this side of the frame, so that's what I'm going to be drawing. So for my free body diagram, we have a small portion of the member from point B to our hinge at C. Then from there, we have our member CD, right? We have this loading going on right here. We have a reaction right here that we already determined the value of 800 newtons. From there, We know once again that this is 400 Newton per meters, but we know that that concentrated force has a value of 600, 1600 newtons found midspan. I'm going to include the dimensions. We know 2 meters on this side, 2 meters on this side. There is a total of 4 meters from here to here. Then from there, on this side, we know that this is point C. We know that this is point D. We know that this is our point B, which is where we decided where it asked us to determine the normal force, shear force, and moment, which is why we did the cut right there. So from there, we have also a uniform loading, or yeah, a uniform loading going on this part right here. We know that it is also of 200 Newton meters. We know that from up here, from point B, which is where we did the cut, to C, there is 2 meters of a distance. So we know that all of this, so from here to here, there is a distance of 2 meters. And I think that's everything. From here, we're just going to be including our normal force, shear force, and bending moments based on our sign conventions. So as you guys know, our cut in this example is to the left. So because it is to the left, we know to start off that our normal force will be going away from the cut. I'm gonna write this as P or also as N. Now, because our cut is also to the left, we know that our shear force will be going upwards. That is our shear force. But I only like drawing it with one side of the arrow, but we do know that that will be going upwards. And then for our moment, we know that it's going to be going clockwise. Oh, sorry. My shear force, I like writing it as V, and then my moment. There we go. Counterclockwise, M. Right? Okay, yeah. Now that we have everything, the next step to determining my shear force, normal force, and moment would be to now finding the concentrated force of this distributed loading that we have here. So as you guys could see, it's going to be the same thing how we found the other concentrated force. So I'm going to call this F of 2. So here we have the force or the uniform loading of 200 newtons per meter. We know that this will be for 2 meters. So multiply that by 2 meters. Once again, our meters cancel out, giving us a distributed loading of 400 newtons. So I'm just going to erase this and simply just add on our 400 newtons. And once again, this is a uniform loading, so it's going to be halfway. So half of 2 meters would be 1 meter. So we have 1 meter from here to here and 1 meter from here to here. Now that we have all of that, now what I'm going to be using to determine the values of my shear, normal force, and moment is I'm just going to be taking the sum of the forces in the x direction, the y direction, and I'm going to be taking the sum of the moments about the cut. So to determine my normal force, you usually view it as a horizontal force, but because of how this frame is, our normal force here does look vertical. So to determine the value of my normal force, I'm going to be taking the sum of our forces in the y direction. So here we have our normal force going away from the cut. So for us, it is going downwards. So that will be a negative force, so negative P. From here, this is a horizontal force, so this will not be included. We have our concentrated force right here. This one is going vertical. It is acting downwards, so that's going to be a negative force. So a negative force of 1600 newtons. And then from there, we have a reaction that is also vertical. This one is going upwards, so that's a positive force of 800 newtons. And those are all of our vertical forces. So we know that all of that has to equal 0. So we end up getting, okay, so yes, we end up getting that our normal force has a value of negative 800 newtons. Right? Let me just double check. Yes. Okay, yeah. Our normal force has a value of negative 800 newtons. So that is our normal force. You could also write this out as N instead of P if that is easier for you guys. Now to determine our shear force, I'm going to be taking, sorry, I don't know why I drew the arrow horizontal if it's supposed to be vertical. Okay, now I'm going to be taking the sum of our forces in the x direction to determine the value of my shear force. My shear force here is going to the left because of our sign convention. So that means a negative force, so negative V. From here we have our concentrated force that is also a horizontal force. It is going to the right, so that is a positive force, so plus 400 newtons. And then, as you guys could see from our free body diagram, those are all of our horizontal forces. So we know that all of this then has to equal 0. From here, we end up getting that our shear force has a value of 400 newtons. So that is our shear force. There we go. And now to find our moment, I'm going to be taking the sum of the moments about the cut, or also known as point B. You know that all of that has to equal 0. So we know here that our shear force and our normal force will not be creating a moment, but we do know that our moment is creating a moment. So here we have our moment going, for us, it is going clockwise. So that is a negative moment. From there, we have our 400 Newton concentrated force. And since we're taking the moment about our cut, we know that this is going to be creating as well a clockwise moment, so a negative moment with a force of 400 newtons. And then the distance, we said that from the concentrated force to here, there's a distance of 1 meter since it is half of our member, so 1 meter. From here, we have our concentrated force of our 1600 newtons. We know that this is also going to be creating a clockwise moment, meaning a negative moment. So we have a negative moment of 1600 newtons. We know that from here to here, there is a distance of 2 meters. So times 2 meters. And then from there, we have our reaction, d sub y. This one is going upwards, so it will be creating a counterclockwise moment, meaning a positive moment with a force of 800 newtons. And then the distance, so our distance from our reaction to here is a total of 4 meters. We know that all of that has to equal 0. So from here, we're simply just going to put this all into our calculator. So let's just start simplifying this. We have negative m minus 400 Newton meters minus 3200 Newton meters plus 3200 Newton meters. All of that has to equal 0. We could see here that these two would just cancel each other out since this one's positive, that one's negative. So then we have negative m minus 400 Newton meters equals 0. So we have negative m is equal to 400 Newton meters, but we want this positive. So our moment has a value of negative 400 Newton meters. And with that, we are done with this example. This is our moment. So with this, we are done with this example. So this example, once again, was asking us to determine the normal force, shear force, and bending moment acting at point B of the frame. So the first thing that we did is we analyzed both sides of the frame. So we knew that our cut was going to be at point B. So we analyzed both sides of the frame to see which side would be easier to work with, since this part of the frame would just need us to find one unknown reaction as compared to this side where we have 3 unknown reactions. We decided to work with this side of the frame. From there, we did our first break at the hinge. And since we know that a hinge support also has some vertical and horizontal reactions, what I did to simply just solve for my reaction at D is I took the sum of the moments about point C or at that hinge to just determine the reaction of my roller support. From there, I drew a free body diagram of the side of the frame that I was going to be working with. I found the concentrated forces of those distributed loadings or that loading that I have on my frame. And then from there, I simply included my shear force, normal force, and moment based on the sign conventions. And then from there, I just simply took the sum of our forces in the x and y direction to determine my normal force and shear force. And then from there, I took the sum of the moments about the cut. So where we did the cut here was at point B to determine the moment. And that is how we've solved this example. Thank you guys so much for watching this video. Please feel free to give this video a thumbs up if you guys found this video useful. And also feel free to subscribe to our channel if you guys would like to see more videos like this one.